Okay, here is part 2 of chapter 11, sampling distributions. So a quick reminder, so we have our population of fish. I took one sample so far, and I got our sample mean 4.375, and which was quite close to our population mean of 4.325. But I just got pretty lucky there. My sample just happened to be close to the population. Now, let's look at the distribution of all possible x bars. So, what is the smallest possible x bar that I could get here? The smallest possible x bar. Well, let's take a look at our population here. If I just by luck happen to get the fish that weighed 2.1 grams and 2.6 and 2.9 and then 2.5, if I just happen to pick the four smallest fish, then my sample mean would be 2 point something. All right, I'm not going to actually calculate it, but it's 2 point something is our smallest possible sample we could ever possibly get. What's the largest possible sample mean that we could get? Well, we could get, if we just happen, just by dumb luck, just get the biggest fish. If we just happen to get the 5.2 and the 6.4 and the 5.6 and let's see the 5.8, then I'd probably have a sample mean of probably 5 point something. Okay, so if I look at the entire distribution of all possible x bars that I could get, I can see that most of my x bars would be around 4 point something, probably, because our sample mean is 4 point something. Or excuse me, our population mean is 4 point something. But it will range from 2 point something to 5. I'll just say 2 to 5. All right. Now let's actually do some more samples. And I set up an Excel sheet here that will do that for us. So here we have our population of fish right here. I set up a sheet like this. So here's our same population of fish. Now you don't have to do this for homework or anything, but here's what I did. I used a command called index, and here I'll show you the syntax here. So index of A2 through A17, that where our fish weights are, and then comma, and then ran between 1 and 16, which randomly picks a number from 1 to 16, and then picks one of those at random. And so I have a 6.4 was a randomly chosen fish, and then the next fish 3.6, the next fish 2.9, the next fish 2.6, and then my sample mean, okay, average of those four randomly chosen fish, okay, 3.875 grams. And then I just copied that, and then I got another sample of four fish right here, and there's the sample mean. Another sample of four fish, sample mean. Another sample of four fish, sample mean. And so very quickly I was able to get lots and lots and lots of samples right here. All right, now if we if we have this large sample of samples, I guess you could call it, you can see just what I predicted. Most of the samples are around 4 point something, some in the 5s, some in the 3s. I don't know if there's any in the 2 point somethings or not, but we can go ahead and calculate the mean of all the sample means. And that's right here. I just did equal sign average of all those sample means there. 4.29, which is almost identical to our population mean of about 4.3. And here's another one. The standard deviation of all sample means. This is interesting. I did standard deviation of all those sample means that I got, and I got 0.78. That's about half as much as the original population standard deviation. Let's go back to our original. Let's see here, where is it? Here we go. So back to our original board here. The population standard deviation was 1.51. Now, the standard deviation of all these different x bars I could get was about 0.75. This brings us to the first rule regarding sampling distributions. And by the way, this is page 293 in your textbook. Let me write it out here. Let's switch colors. Let's switch to blue here. So if here's the first rule. So if you take a simple random sample of size n uh, from a population. Now, the population itself does not have to be necessarily a normal curve. It might be normal, but it doesn't have to be. All right, from a population with a mean of mu, and the standard deviation of the population is sigma. Okay, so if you do that, and we did that with the fish. We had a simple random sample of 16 fish. We took a random sample of size 4 fish from a population of out of all the fish in the fish tank. Okay, then it turns out that the distribution of all possible x bars, which there could be millions and millions of possible combinations of different samples. They give you millions and millions of different x bars, but the distribution of all the x bars has a mean that's the same as the population mean. So as the mean mu. So that's the mean of all the sample means, of all the possible x bars. So the mean of the means is the same as the population mean. So it has mean mu, and standard deviation is sigma over square root of n. Okay, so in the example that we just did, our population standard deviation was 1.51. So population standard deviation 1.51. Our sample size was 4. So what is the standard deviation of all the possible x bars that I could ever get? Standard deviation of all possible x bars. Now remember, this x bar that we did, 4.375, that's only one of many possible x bars. Well, I set up an Excel sheet like I showed you of many, many possible sample means that we could get from this population. And it turns out that the standard deviation of all those different x bars that you could ever get from this population, hold on here it is. You can compute it by the formula here, sigma over square root of n, which is sigma 1.51 divided by square root of 4, which is square root of 4 is just 2, so 1.51 divided by 2, which is about 0.75. We can get a more precise number here. 1.51 divided by 2, 0.755. All right. Okay. That is the standard. That is called the standard deviation of the sampling distribution, right there. Now, what does this number tell us? Well, we know standard deviation in general means how much variation you have among your individuals. But in the context of a sampling distribution, standard deviation tells us how much variation do you have among the possible x bars you could get. So this 0.755 means of the amount of variation in all the potential x bars you could get. And the smaller, the better. You're hoping for small standard deviations here because if you have a large standard deviation, then you've got a whole lot of variation among your x bars, and your x bar is not going to be a very reliable estimate. But if you have a small standard deviation, uh, of the distribution of the sampling distribution. Remember, the sampling distribution is all the different x bars you could get. So if you have a small standard deviation, that means that your x bars are usually very close to mu. And that's the goal of all this, is to get an x bar that's close to mu. Now, I want to mention one more thing here about this part. This part gets overlooked sometimes here. It's back to our rule. If you take a simple random sample size n from a population, then the distribution of all the possible x bars has a mean of mu. So what that tells us is, back to our Excel sheet here. So if I look at all the samples that I took on this Excel sheet here, some are too low, some are too high, some are about right, but on average, the sample means are just right. That's what this says here. The mean of the distribution is the same as the population mean, which brings us to the concept of an unbiased estimator. This is mentioned in the textbook on page 293 as well. But the sample mean is an unbiased estimator, which means that on average, it's just right. On average. Sometimes it's too high. Sometimes the sample mean is too high. Sometimes sample mean is too low. But on average, it will be the same as the mean. Same as the population mean. Same as mu. And that is it.